Calum got his PhD quite recently from University of Hertfordshire. Before that, he studied theoretical particle physics from University of Sussex, but as he says, found the stuff too weird for his brains. So he became an astrophysicist, obviously.
It's easier.
So he currently works at University of Hertfordshire, but will be going to Universidad de Valparaiso in Chile in a few months as a postdoctoral fellow. His main research is how, where, and when stars get made, though he has worked with evolved stars, stellar variability, and white dwarfs. And one of his other things, non-astronomical things that he does, is that he really likes a lot of motorized stuff, and he has a surprising lack of skill in it, but he has done motorsport racing.
Yeah, I drive a little Formula Ford, it's fun.
Yeah, Formula Ford.
It's old.
Anyway, thank you very much, Calum, for giving a talk today. And before we start, I'm just going to do a very quick head count. How many of you are from Rothamsted?
Rothamsted or Harpenden?
Rothamsted, yeah, from Rothamsted. And how many are from Harpenden, if you want to say? Okay, that's like most of them. Thank you very much, and thank you, Calum.
All right. So, hi everyone. So, this chat is going to be focusing on my last paper, but including, it's based on a talk that I just gave at a conference, but what I've done is I've removed a lot of the very boring numbers that I hate having to put in there anyway, and replaced them all with nice pictures of space. I've also put in a little intro to try to make sure that people who are normally expecting conversations about wheat, I hear it's a popular topic at this institute, to give you a bit of a rundown on what stars are, how they work, and how it is that you go about making them, so that the stuff I will actually talk about makes some degree of sense. So we'll start off with just a nice picture here. This is Cygnus X, which is a star-forming region that I've been working with, or on, really. It didn't join in, really. It was just there. This is the image taken with the Herschel Space Telescope through the High-Gal survey, combining a bunch of different mid-infrared wavelengths. And I guess we'll probably have to discuss that.
And how old would it be?
So, good question. So the age of Cygnus X depends on which cluster you're looking at. The age of the stars in it is, what, a few 100 million years-ish, maybe 100 million years, thereabouts.
Very young.
Very, very young, yeah. So it's a new area full of new stars. Certain bits of it are very, very young indeed. There we go. So the basis of astronomy concerns, not some people say it's machine learning and boring computery stuff and possibly stats if you ask Mike, but I prefer to use telescopes because it involves going to places like Hawaii and La Palma, and that's a free taxpayer-funded holiday. Basis of it is that wiggly line at the top, the EM spectrum. I assume most of you are familiar with the concept that light is more than what we just see with our eyes. Useful thing is we have telescopes for all of it, as well as, obviously, telescopes for X-rays and gamma rays, not so much, and it's not on Earth. You've got these things, Cherenkov arrays, but they're very weird because generally X-rays, gamma rays, and most UV radiation doesn't come through the Earth magnetosphere, which is good because otherwise we'd all die of a myriad of unpleasant diseases. But downside is we can't really see what's going on without putting telescopes into space. But space telescopes are great regardless, so a lot of other kind of wavelengths are also serviced in space. The only ones that aren't are radio and submillimeter. Submillimeter, that's just a rebranding job. If we ask somebody who's going to give us money for a great big microwave dish, they tend to scream and run away, and they don't give us cash. Now, we like cash, so instead we rebranded the whole microwave regime as submillimeter. They have no idea what it is, and they give us what we want. So something like Alma there, which is in Chile, it's in the Atacama Desert, and apparently the area around it, I only found out recently, is often run by criminal gangs. So that was fun. I'm moving there soon, so. But I mostly work in the infrared. That's my main area of expertise, but I do some optical stuff as well. I've done some X-rays, I found it baffling, and I never want to do it again. Although, according to my CV, I'm always happy to do X-ray work, because you can complain about it later. You know what, I'm just going to move over there. Technology is not my friend today. So here is one of the telescopes that I would have used once. The Subaru telescope on Mauna Kea. Yeah, they don't just make mid-priced saloons, they do also make giant telescopes. But this is a near-infrared telescope, and near-infrared is traditionally how you go about finding young stars. It is generally the best wavelength to look in, although Mike and I would both maybe disagree and say it's maybe the mid-infrared, which is a bit different. But near, mid, and far infrared, they're just progressively more and more red. If you think about...
Young, though, I mean, you're talking relative to the Earth, or relative to...
When we say young stars, we mean relative to the age of a star. An average star like the Sun will live for about 12 or so billion years, and by new or young stars, we tend to mean anything from, well, I guess a few 100,000 years up to maybe 10 to 100 million, depending on exactly.
Effectively, you've got stars that will be new today, but will be outside. We'll never see them because they're so far away.
Yes, but within our galaxy,
That's in the time.
yeah, there's a bit of time, but don't forget the whole there's a confusing redshift and general speed of light is a set speed. Space, really big. As a result, it can take a little bit of time for something that happens physically now for us to observe. Cygnus X, for example, I've got a number on the screen of how far away in time it actually is. So I will get to that when we get there. So what is a star? Because figured that might be a useful thing to start with for those who don't know, or beyond, it's shiny either at nighttime or daytime, depending on which star we're referring to. Here is a little diagram of the Sun, the laser pointer here, for those who can't quite work out that it's clearly this big ball here. A star is a great big ball of hydrogen, basically. It's hydrogen plasma. This is not the same as plasma when referring to as blood. I often get that question, normally admittedly from 8-year-olds, but best to cover it off anyway. This is just another additional state of matter that is what happens if you heat up gas beyond its... what is the word? Like, you boil to get gas. Is plasmificate? That doesn't feel like a word. If it isn't, it's going to make it... Yeah, it's the hottest one that exists. Yeah, well, fourth state for that effect. You can go further in the other direction, but super solid, super liquids, they're a bit weird. So plasma, normally if you try and heat up gas, what does gas do? It expands. And for the most part, it will just... Yes, but in theory, if you just stop it from expanding by putting it in a box, you can prevent gas from expanding, and then it will eventually turn into a weird magnetic and electronically charged ball, where you separate all its constituent parts and they kind of live in a weird soup. But what's cool is that you can make anything into a magnet this way. You might get taught at school, there's only 4 magnets that you can make, iron, zinc, and all that jazz. Well, no, you can make anything into a magnet. Just warm it up enough and spin it. And then you could turn a tree into a magnet if you felt that way inclined. So anyway, that's a sun. They work by gravity squashing them down, and that gives them energy because you've basically got gravitational potential energy pushing you. If you get pushed, what do you do?
Push back.
Well, let's assume that whatever's pushing you is stronger than you are. What's going to happen? You're going to move, right? Well, in theory, once you get to a point where you get strong enough, maybe you're being pushed at, say someone pushes you one way, someone pushes the other way. Exactly the opposite direction. Then where do you move? You get squished. And if we can't squash you anymore, instead you'll warm up. And that's why they're hot. And that constant generation of heat pushes back the other way when you include something called nuclear fusion, which is taking hydrogen and another hydrogen and smooshing it together. Obviously, Mike knows that I'm talking nonsense here because you actually require deuterium and tritium and you gradually add hydrogens to it. But for the sake of it, let's just say 4 hydrogen atoms, which each have a weight of 1, you smash together and you make one element 2 called helium with a weight of 4, except that it's not quite 4, it's a little bit less than, well, it's a bit more than 4, but hydrogen's a bit more than 1, right? Point is, there's some free energy involved. The numbers don't quite add up, and the number that is missing becomes energy, which we see as explosions because of E equals mc squared. I won't give you the full equation. I only found out that that is not even the real equation. Yeah, because you've got to include an additional factor from the momentum of a photon, which, baffling. Anyway, point being, you get free energy from stars. Happy days. That pushes against gravity and you form a nice little ball. Over time, they'll use up their hydrogen and they'll be left with mostly helium, and they'll become what we call a red giant because the core will need to condense much further and the edge of the star will expand. When that happens, they'll be quite big. Here's the sun to scale with the sun as a red giant. You will notice that that is quite considerably larger. Bad news if you live on Earth when that happens, but luckily for us, that won't be for another 3 or so billion years, right? I think so. Around that. It's ballpark. We're astronomers, we're never really sure. We consider like 1, 2, and 3 as the same number, so. Not like particle theorists, they contain everything as 1. They're absolutely baffling. Speed of light, 1. No, it isn't. It's just a lie. Right. We call this hydrogen burning phase the main sequence. Why do we do that? I will skip through. Here's a plot. Look, science. I didn't make this one myself, but there we go. The main sequence is this bit here, where we find normal stars. Over here we find the evolved stars, and over here we find dead stars. Now, ordinarily this will make no sense, and look, numbers on the side don't help one jot. Except that they basically do. We'll ignore colour, because that is a weird construct that astronomers kind of like to use, but it can be quite helpful. But you can consider this instead as temperature. This over here is cold, and that over there is hot. How cold? This is somewhere around maybe 50, 60 degrees on one end of the axis, so a balmy day, all the way over to hundreds and hundreds and hundreds of millions. On this axis here is just physical size, not mass, size, bigness. Very, very small. This, for example, over here is roughly the size of the Earth, and up there is quite a large amount bigger than that. Very, very, very big stuff. Stuff in space can get quite big. Now, this is all for stars that have finished being produced. If we want to observe the youngest stars, they are not yet on the main sequence. So instead, we would find them over on a little bit of the diagram over here. This is looking at a already completed cluster, so there's no young stars left. But if there were, they would live down here, and we're on what we call Hayashi tracks. So where is it that we actually find stars? Here is a lovely picture from JWST that you can stare at whilst I talk at you. Now, stars, we find them all over our galaxy, right? They're everywhere. But where do we find them in groups? Well, they tend to form, or at least most stars will tend to form in clusters. Some do form isolated out just in the middle of nowhere. The sun, we think, is actually among those group of ones that didn't form with friends, because if we look up at the night sky, we don't have stars these sort of really close distances to us. But for the most part, the majority of stars will form in a great big gas cloud called a nebula. Now, we'll get onto the use of the word nebula in a minute, but we often also, well, scientists, people like me and Mike, we will call these star-forming regions, because this is a region with which you will form stars, creatively named. And this is just a great big ball of fairly cold hydrogen that has partnered up with another hydrogen friend to form just a standard, I want to say covalent bond? It's covalent, right? I haven't done chemistry in a long time. Oh, are they separate? There you go. I dropped out of chemistry at like 16, so. Point is, these are what we call molecular hydrogen clouds. And inside there, there'll also be some other elements floating around, which governs how much metal you find in stuff. And these clouds will move, and you can see that in this image. This is with the JWST, this is what $6 billion gets you. And you can see even looking at little waves like this, these ripples, they're all moving. And if you've got areas of a gas cloud that are moving with respect to one another, you're going to get areas where you have more density and less density. Areas with more density have more mass. With more mass, you have more gravity. And that gravity will cause more motion, which can cause collapse, because these clouds are not fully stable. And as soon as you've got gas collapsing in on itself, you've got the ingredients for a star. And that's all there is to it, really. Once you form a ball of gas, that gas is going to warm up because gravity is pushing it, and it will keep warming up until it starts doing nuclear fusion and then can push back against gravity. That process takes a few 100 million years, thereabouts, depending on the size. Big stars will form very, very quickly. We'll do it in 10, or even 1 million in some cases, I guess, for the really, really big stars. Although we don't know how that works, because astronomers can't actually see it happen. They are very, very hard to spot. No, that projector one doesn't work. All right, now nebulae look a bit different depending on which one you're looking at. If you look here, the Orion Nebula should be familiar to most of you. You can actually see, or if you look for Orion's belt, you'll see 3 other stars directly below it called Orion's scabbard, and the lowest star in that scabbard is in fact that thing. Not 1 star, but several thousand. Although the light you're seeing from it comes from, what, 7 stars in the trapezium, I think? Yeah, which are those bright ones in the middle. These are basically finished forming. They're done because they're the biggest stars in the group, and they are illuminating this cloud of gas both in front and behind it, which means we can see all the light from it because it hits the back of the cloud and then bounces back to us. Because big stars tend to emit in UV, and I guess one of the things I didn't mention about the wiggly line from earlier, the photoelectric effect means that if we hit something with a photon with high energy into something else, that's going to take some of the energy out of the photon to warm it up. And then as it releases that energy, it then has, well, that light again, it'll have less energy in it, and thus will move down your EM spectrum. So light that starts optical will go into the infrared, light that starts in the UV will go into the optical roughly, in a manner of speaking. Obviously not perfect, given the actual maths involved with that is awful, but something along those kind of lines. It's a good rule of thumb. Here's a very nebulous term, nebulae. It's an old word that basically meant, hey look, there's gas in space. But when you did, hey look, there's gas in space in the 1800s, there's lots of different ways you can put gas in space, and in a kind of much the way the Father Ted sketch about is it a small cow or is it just nearby or big cow further away? Well, same kind of thing. Any gas in space will look the same until you know roughly how far away it is, and then you can get an idea of scale. And for that matter, that's why we have things like planetary nebula, which is not a planet, nor is it a nebula. You have reflection nebulae, which is just floating gas that's near a star that's, well, physically looks quite far away because they're both quite nearby, and if they're nearby to us, the gap between them on the sky looks big, even though the gap between them in reality is quite small, because obviously the further away you look in space, the smaller the separation between things. You also have, for example, in the Messier catalogue of nebulae, you will find M23, the Andromeda Galaxy, which is not a nebula, it is a much larger galaxy that exists, but, oh yeah.
What is a planetary nebula?
A planetary nebula is the leftover remnants of a small to medium-sized star. So big stars explode, stars like the Sun do not. They basically stop doing nuclear fusion, leaving a very condensed ball of carbon. I'll leave you to work out what a condensed ball of carbon is actually made out of. Hint, it's very expensive and some South Africans would probably want it.
So, does it actually form planets, or why is it called planetary?
It's called planetary nebula because it looked a bit like a planet. It's one of those things where we just haven't renamed it since we've worked out what was going on. Generally, scientists are loath to rename or redo anything for historical reasons, which any new person getting into the field is like, why are we not changing this? Like me coming from particle theory, I found this baffling. The magnitude system, how we measure the brightness of stars, which does not even start at 0. Yep.
I was thinking Pluto.
Yeah, the only upside for Pluto, well actually wait, no, I won't give the joke I normally give about Pluto, because I know there's at least one American in the room. Yes?
Where does the gas from the nebula come from?
That was just sort of, well, it generally is the Big Bang. Big Bang nuclear synthesis created, so basically the Big Bang happened 13.8-ish billion years ago, depending on what value you use for the Hubble constant. And this formed hydrogen, helium, and some lithium, and I guess a bit of beryllium. Beryllium is a questionable element. You'd have to go and ask someone at my university who's much better at this than me. No, so Jackie, she's amazing. But in everything from that point, anything bigger than that was formed in previous generations of stars, so that when you form a star which, for example, has lots of carbon around it, what need could we as people need to understand why carbon is important? Yeah, it's us, right? We're predominantly made of carbon. Carbon is our thing. The sun hasn't made any carbon. The sun is making helium. the gas cloud that made it originally started with just hydrogen, helium, some lithium, and beryllium. So where did the carbon come from? It had to come from a previous generation of stars, then injected their material through things like planetary nebula, as well as big winds from kind of stars, a bit like those red giants, only they're bigger and they wobble. They pulsate for reasons that I'm not going to get into because it's a very different talk. And also so much more boring. It's a talk I have written, it's just dull. Based on feedback.
But the heavy metals all came out of supernova.
Yeah.
You can't get heavy metals above a certain level.
Technically you can. It's just one of those things that's entirely maths. The slow and fast R process will make you significantly amounts of large metals that you can then produce with AGB stars without supernova.
Test the maths on.
Yeah, it's... I tried doing the maths on the slow R process. It is too big for my brain. But yeah, you can... There's points of high temperature around the edge of stars where they kind of, where the magnetic fields interact. And that can produce really heavy elements, but localized. Anyway, not important. Here are some more pretty nebula. They've got bubble nebula there, which is a planetary nebula. That's what they look like. And then a reflection nebula over there. Now, these were all taken at Bayford Observatory by our own David Campbell.
So what makes the bubble? Is that basically expanding from an explosion?
Expanding gas from not an explosion, but the cessation of nuclear fusion. There's basically residual radiation pressure.
And it's gone out like that.
White dwarf formation doesn't collapse. They gradually will just, their edge of their envelope is now so far away from the core and they've lost so much mass to wind that gradually things will just start to float away under radiation pressure, which, if you have it in every direction, makes a bubble. Different elements will move in different ways though. The elements that were formed earliest and what residual hydrogen they have left, because it is lighter, will move faster because it is also starting further away from the star. Hopefully that makes some degree of sense. Now, on to star formation, yes. No, don't apologize.
Previous picture, are those colours actually there, or is that?
Oh, sometime, right. No. It depends on what kind of light you looked at. So astronomers generally will use false color pictures. Now these are optical images, so we are closer to looking at the right stuff. In this case, this collection of reds and pinks would mostly be red. It would just be a lot less vivid than we see here. You would have to be very, very close to it and with a long exposure eye. Because our eyes are video cameras. We can't expose for an extended period of time. Whereas, obviously with a camera, you can. So if you put, this is I think about 5-minute exposure. And if you had eyes that could withhold light for 5 minutes, you would see that if you were there. It would just be a bit more browny red than red and pink. This one over here is all made of narrow band photometry, which means instead of looking at a color, you look at an element. Every element has a color of light that will go. Those of you that work in research will know this through mass spectroscopy. We do the same thing through space. We just can't do what you normally would. You can't put it in a vial and spin it around and shine a light through it. So we have to put it through a prism and then put it through a diffraction grating, and we can do the same thing. But you can also make a filter that just lets through a specific wavelength. Do the same thing, and then you can look at specific elements. In this case, the blue in that image is oxygen, oxygen 3 line, popular for planetary nebula, highly energized oxygen. It's very, very hot. The green is from H alpha, and what residual red you can see, I think, is just red light. You can also do a combined one using sulfur, but I think the filter was not on that telescope that day. Anyway, on to star formation. These are real pictures of newly formed stars. Now these are mostly in the constellation of Taurus or Lupus. They both are very nearby, physically. Not the constellations, they're also just on the sky. But star forming regions within those constellations are quite close. Orion is one of the closer ones as well. Cygnus is also very close, but not quite close enough to get images like this just yet. Well, actually, maybe with current telescopes it might be. But this here is taken with ALMA, the sub-millimeter microwave observatory. This is an image, I suspect that one is... that's T Tower, right? I'm pretty sure it's T Tower. which is the archetypal YSO, young stellar object. That's the term I'm going to use because that's the term that covers both protostar and then things that aren't protostars but aren't full stars yet. As you can see, there's a wide variety of shapes and sizes, not sizes, but shapes of their disks. This disk is all the leftover material that they have from their formation. It happened in a cloud, and if anyone's ever tried, well, you can see the same physics. Sit in a bath, take the plug out. As water starts to flow out, over time it will start to spiral in on itself because it's trying to conserve angular momentum. Do the same thing here, same physics.
Say that again.
It's the conservation of angular momentum. So as soon as you drop your...
So you've got space,
Yeah.
you've got hydrogen floating around,
Yep.
being pulled gradually together. Where does the rotational...
Because they're all coming from different directions in that cloud, and they always had their pre-existing motion. That gas is not it's not steady. So they will have a residual amount of momentum that once you put in a gravitational body...
Overall, there's a net bias towards one direction to cause the spiral.
Yeah, and depending on which direction was the favoured one, I mean, it changes depending where you're on the cloud. Things will spin, but they'll just...
You've got Big Bang, and you've got everything just going out like that. What I don't understand is
Oh.
why there's a net. If you look at the average...
Because once you move into a galaxy, you have dark matter that helps condense stuff into channels and filaments. And inside those, they will be channeled towards supermassive black holes, and that imparts a residual momentum in any given direction, and then gas moves along those, and then you start to collapse bits and pieces here and there, and it basically just ends up with individual clouds have somewhat slightly biased one way or another, and then that can change depending on if there was like a small bit of motion in one part of a gas cloud pushing up this way, and a smaller motion pushing down that way, you're going to get a residual motion to want to spin clockwise or something.
So across a trillion particles, a little bit of difference ultimately ends up with that.
Yep. And eventually they'll collapse down because then you start to move towards more conventional physics, which will start them like cones and finish them like disks. Ones with wide, kind of yo-yo shaped, old-fashioned yo-yo shaped disks, they are younger, and the later ones over here. I'm going to try and not use terms like older and newer, because depending on the size of the star, one that might be younger might be more evolved than another one. It's very confusing and very annoying. Why can't stars just form at the same speed? It'd be so much more helpful. But you can also see cool things like that. There are gaps in this disk. Why are there gaps? That's a question for you guys. Who here has an idea as to why there might be gaps in a disk? Think about, I know you know, Mike.
Well, if you look at Saturn and things like that, it's all to do with sweeping out. We've got the basically sweeping out with other things going round in
There you go, okay. What things go round in circles around stars?
planets.
Planets, yeah. So what you're seeing here is the formation of new planets happening around a very, very young star. And you can see this not just in, I'll get onto the YSO classes in a minute, but this more evolved YSO, but you can also see them in younger YSOs. Now this one doesn't have any, but we can see in certain resolved images of really, really, really new young stellar objects, planets forming. We think they form basically at the same time you make stars, which is really quite interesting. Because it basically goes to show as long as you've made a star, you have made planets. And if you've got planets, question mark, aliens.
So Jupiter, which is obviously a hydrogen,
Yep.
could potentially be a young Jupiter going around there.
Oh, yes, over here, definitely. I would wager there are two, probably one here and one there, most likely, which is why you've got a much bigger gap in the middle, but two distinct rings that join into it. I would guess you've probably got two proto gas giants. They may collide, yes.
Where do the heavier elements come from planets?
So things like iron, they were previously made in a supernova explosion. That supernova explosion pushes material that was made in that star through the cosmos, either directly into surrounding gas, or over a much longer period of time through what we call a superbubble, will move from one nebula to another nebula, and so on and so forth.
So the materials are all basically already there.
Yes, the original material that formed your galaxy, the oldest stuff is in the middle of the galaxy, and then star formation spreads outwards through spiral arms or whatever bubbly shape that your galaxy is.
Good book, you are Stardust.
Here is another image of a young stellar object. The other thing to note is that central area, so not So in the previous image, you couldn't really see the star in the middle. What you can see instead is the inner disk. Now here we can, basically using an artist's image, excellent artist, is actually an astronomer, but they're just very good at drawing. So ESO, I hope ESO pay Martin Cormas and Leo Casada for their work, as opposed to just using it on their outreach site. But this inner area here is what we call the inner disk. And that is the material that is going to gradually fall onto the star and make it bigger. So your mass is going to keep increasing. And that rate is roughly constant, except when it isn't. For one reason or another, either the magnetic field of the star might change, it might increase in its magnetic field strength through convection in the core, or it might simply change polarity, and that will cause a change in the disk structure, and that can lead to more material falling onto the star. When this happens, it gets brighter, which is very interesting, because if the star's getting brighter, what's it doing? If it's giving out, hotter, perfect. It's getting hotter. And this can be in a very big way, which we'll get onto in a bit, but it's worth bearing that in mind.
So what happened in the clear sections? Has it condensed into something?
Yeah, it's condensed into most likely a protoplanet that's going round in a big circle, hoovering up all the material. Now we break YSOs down into 5 classes, which are helpfully named 0 to 3. Yep. I'll leave you to wonder why we don't just rename them. Originally we had classes 1, 2 and 3. That made sense. Then we realized that actually 1 and 2, there was a bit more wiggle room between them than we thought, so we put a new one in there, which are called class FS, or flat spectrum. And then class 0, when we started looking for the same things but with submillimeter telescopes, and found some that we couldn't even see. So then they're even younger, so we had to go back from 1. So 0 it is. And we classify them by this thing here called their spectral energy distribution. That sounds scary, don't worry. All it is its brightness in SI units, which is annoying for us astronomers who don't normally work in SI units. We have to go and convert everything, and it's a massive hassle. Across a multitude of different picture wavelengths, basically. If we take optical light, mid-infrared, near-infrared, and maybe some UV, we can build a wiggly line that basically governs how bright a star is at a given wavelength. And as we move in sort of this direction, we can see which is which. This is long wavelength, that's short wavelength. I know it's backwards to the way you'd normally see it displayed, but astronomy things. Class 0s are in the collapsing ball phase. Class 1s, which actually is more like this picture than that picture. They're, well, yeah. So these are much, much broader. Then you have that sort of trademark shape, and then you finish with a very, very flat disk. These look like normal stars with just a teensy bit of additional infrared light. These are basically a bit like the Oort cloud we have in our solar system that contains all the comets. Just take that and scale it up. But otherwise are the same thing. For most of us that actually study normal YSOs, we don't care about class 3s. They're just not interesting. They're in your sample, we're like, yeah, well, it's in a young cluster, so we have to include it, but we don't really want to. Here is some cool stuff that I didn't have another place to put, and I wanted a nice pretty picture on the slide. This is a JWST outflow. This is a fairly new picture from JWST. I only saw it for the first time last week. Now, this is an outflow coming from a class 1 YSO. Because if you have a point when you are suddenly what we call accreting, so more material is falling onto the star than it was previously, if you do that at quite a considerable amount, more than usual, you will instead need somewhere to put all that extra material. And because these stars are magnetic, they can act like great big space ray guns, basically, and blast that material off into space. Again, there is some more physics at play that I'm not going to explain because it's boring and involves lots of, it's a dull equation. But the pictures are cool. And so this is one, just a chance alignment shot where you've got this outflow coming from a star that's over here-ish, and that is now looking like it's heading towards a background galaxy. So we're looking at a shot inside of Milky Way, and then suddenly they can see another galaxy megaparsecs away. I will get onto parsecs in a moment, don't worry about that. I realised that I haven't explained the actual unit of distance astronomers actually use. Hint, it's not light years. So these exploding, not very much explosively bright young stars, we call eruptive YSOs, and they come in, if you ask most people, 2 flavors. Obviously, it's not 2, it's about 5, possibly more, depending on how much more we find. But they come in all different shapes and sizes. For the most part, fjords look a bit like this. They start off very, very dim. Oh yeah, for reference, the magnitude system is baffling. Don't try and understand it, because I hate it as well. 16 is lower brightness than 12, which is brighter, but isn't that bright. And each time you go up by 1, you don't go up by 1 factor in brightness, you go up by a, what is it, minus 2.5 log of something or other. It's a silly system. Point is, it's getting a lot brighter. And by going up from 16 to 12, you're going up by within about 4 orders of magnitude in brightness, so it's a massive increase. So that will obviously have massive changes to the temperature of a star, and thus the temperature of any planets that may be forming around it. Now this doesn't seem to happen that frequently. They aren't really known to repeat, although recent work has at least come up with a recurrence timescale of maybe once every 1,000 years or so, although not based on any observation of one actually doing that, because humans haven't been doing astronomy long enough to actually notice if that happens. And then you have short period sources, short duration sources called XORs, which last anything from a few months to a couple of years, are much smaller and are driven mostly by magnetic field changes. Fjords are driven by the gravitational collapse of a big or small part of their disk, either caused by a planet merger, a planet with a decaying orbit, possible tidal interactions between parts of the disk, or more exotic things like interactions with other stars. In your cluster, you form quite close together. If one moves past you and it's got more gravity than you do, it's going to mess up your disk, and then it's going to wobble, and then it's going to collapse. And the only place it's going to go is onto the star, not like a nice little whirlpool, but instead like a stream, and that will cause it to get incredibly bright. Hopefully that makes sense. We identify them through their light curves and also their spectrum. So we look at what elements are in it, what those elements are doing, and what it looked like when that happened. And that is how we work out what's what. And finding fjords is a big deal, because until, well, when I started my PhD, there were 14 of them known, and now I'm done, there are, what, about 40, and in my last paper, I may have found another 15. Paper I did with Mike. He was very helpful, mostly because I used one of his catalogues. Right, here is Cygnus X. Pretty picture. We can relax again for a moment. This is Cygnus X as seen with the WISE satellite, which is a NASA facility that's now sadly dead. That is a mid-infrared camera that originally was intending to take, 4 pictures in 4 bands and leave it at that of the whole sky. And then something broke, so instead they used it to find asteroids, but in so doing they took pictures about once every 6 months for about 10 years. And helpfully for the rest of us, those pictures include the rest of space, so we just sort of stitched them together. And then we can work out exactly what's going on in areas that are very, very much deep into the gas. The deeper you want to look into gas, the less optical light gets out. And instead you're looking more and more into the mid-infrared, which generally is not what people do for YSOs. They use the near-infrared. So I had the idea to go and have a look in the mid-infrared to look to see if there are more eruptive events, because I figured, as did a couple of other people beforehand, but then never bothered to actually look into it, so joke's on them, I did it, are there more of these big eruptive events in younger clusters when their gas disks should be more unstable, they should be closer to their friends, and indeed enemies, as well as having higher magnetic accretion rates anyway, meaning these big events should be more likely. And I wanted to codify that, and to do it, I thought Cygnus X, because it is relatively nearby. It is at 1.5 thousand parsec, which is approximately 4,600 light years. I had to look up that conversion. Astronomers don't use it. We have to occasionally learn the conversion because Star Trek makes everyone think that's what we actually use. Parsecs are just something at 1 parsec away moves by 1 arc second over the course of 6 months in the sky. So 6 months, Earth goes around the sun, we go from one side to the other, and if you think about binocular vision, close one eye, close another eye, things move, right? That's called parallax, and that's how we as people work out how far away things are. That's how, if someone throws a ball at you, you could in theory catch it. I can't, I'm a nerd. It would just hit me in the face. But I will notice it's coming at me and then not know what to do. Now with that kind of covered, something at 1 kiloparsec will move. If we take a shot every 6 months going around the sun, things will do the same thing. If something moves by 1 arc second, which is 1/3600th of a degree, we therefore know that is exactly 1 parsec away, and we can measure distances like that. The mass of Cygnus X is big, 10 million m-sun, because we don't measure things in kilograms either. Kilograms are meaningless numbers in astrophysics. I can't picture how big a star is in bags of sugar. It is impossible. However, I can picture the sun. The sun is big. It's that big. It's as big as the sun is. And if something is like 2 m-sun, great, it's like the sun, but there were 2 of them. Brilliant, easy to understand. In this case, 1 million suns is kind of hard to picture, but it's at least more reasonable. Point is, it's big, and it is comprised of a whole bunch of different individual components. There are 6 of them. If you're interested in reading more about that, wait until Mike's finished his new paper. There you go, now you have to hurry up, because I've told people about it. Yes?
And I'm going to ask the novice question. Why are some of your star clusters in different colours? Because I don't know anything about the colouring in.
The colouring in, we mostly choose for effect. This is a mid-infrared picture. If we were to look at it, we would see nothing, except stars.
Yeah, I figured that.
Oftentimes these would look like dark clouds in space where you see nothing at all. But because we're looking in the mid-infrared, we obviously need to colour it so that we can at least see it now. On the computer, we can just tell it what colour we'd like to make certain elements of dark colour.
You can pick certain aspects
Yeah.
of that picture.
So in this case,
Colours.
the dark red is the coldest light.
Okay.
So this is, in this image, that is what we call W3, which is about 12 microns. For those who are familiar with mid-infrared, it's very mid-infrared.
Cold light.
Cold light, that's colder. The stuff that is green is more warm. It's still very, very cold. It's still below 0 Celsius, but it is warmer.
Okay. Thank you.
No worries. So here is the actual science bit now. You've at least understood enough about what I do as a job that I can now quickly tell you what the whole paper was about. The idea, as I said, was to look for more of these eruptive sources, and I wanted a good start point. I figured Cygnus X was a great choice. Mostly because I'd already accidentally found a few interesting things when I was looking to bulk out my PhD thesis. COVID had happened, I couldn't do one of my science chapters, so I had to get creative. And in so doing, I found a few interesting things, and I thought, okay, what if I do a test? Basically, my boss was in charge of finding if stars in the northern hemisphere, including Cygnus, had gone up in brightness between the 2 or 3 years of his survey. I decided what a more interesting thing to do would be to look for the locations of known young stars, but look for times when we only saw them once. Now this was a very boring job, because the most times this happened was because the picture was rubbish, unless it wasn't recorded, but it was still there. It's just that there was like another bright star nearby, or a cloud had got in the way. But a few of them were really, really interesting. And then I was like, okay, if I found a few, I can probably find more if I now actively go and look for them. So instead of writing up my conclusions to my thesis, I did this instead, which upon reading my conclusions, my external examiners asked, what were you doing when you should have been doing this? And I was like, hey, here's a draft paper. Is that even in the thesis? No. No, it is not. But look, it's almost done. Then they gave me a look that says, we're going to pass you, but we're not happy about it. Anyway, I examined 2003 young stars. With my own eyes, it was very dull. And from them, I found 29 candidate eruptive stars, which in a field of 2003 is loads. Normally this is about between 0.5 and 1% that you would expect. And we got, actually a pretty good amount. So that's quite nice. About an order of magnitude more than is expected, which is a pretty big finding. 12 of these appear to be new fjords, subject to upcoming telescopes if I get time on one of NASA's facilities. I did ask, I even asked nicely. Mike read it, I said please and everything. Not that that will help. I also had to fill it with figures and maths, and it's very dull. Anyway, here is a selection of their light curves so you can kind of see what's going on. With most of you, excuse me, to practice doing transitions. Morph, it's great. Here are the 3 of the 12 kind of Fjord candidates. We now immediately know that this isn't one, but it looks like one, and that's weird. This, according to its spectrum, looks like an XOR, but its light curve looks like a Fjord, and that's strange. We've only seen that a few times. So we want to understand why it's doing that. This one here has a very long build-up time, and this one here looks traditional. So all good. Yes, it works, and we find some more stuff. These ones are much shorter than usual, but they still look like Fjords, but they look like they've been sped up. Instead of lasting a century, they seem to last about 20 years. We don't know why that's happening. That's new. In theory, it should take longer at younger ages because you've got more gas to fill, so it should take longer to go down. Again, don't know why this is happening. And these are what the sort of short period sources look like. Little blips every now and then. Now, an important next step is to compare this finding to a normal sample of young stars in order to prove that it's not just Cygnus, it is instead the theory about the age of the stars you're looking at. And handily, there's an excellent catalogue of pretty much all the young stars in the Cygnus region, created over there in 2021. At this point, I'd used this before you'd even joined Hertfordshire. And it's like, so someone's joining. Who is it? It's Mike. Oh, the spicy man. Ah. And then I said hi. And then you looked very weirded out at the PhD student that appeared in your office without prompting. I would say young, but I was still depressingly old. Anyway, this examined 5,000 and more young stars, and I found 500 of them that were worth looking at, that I then had to painstakingly go through by eye and examine. And from them, we found 19 that well, actually I found a bit more than 19. We actually found 24, I think, but the referee from the paper wasn't so happy with 5 of them, so told us to take them out and put them in the appendix, and that's fair enough. Anyway, so of these, found 19 of them, but 19 from 5,000 is still less, which is good. And if we were to then include class 3 YSOs as well, we would then see that number trend back towards 1%, which is exactly what we wanted to find. So, yay, science happened. I at least did something with my grant. Here are some spectra of some of the stars that we looked at. You can see one up the top. Well, actually, you can't see because I didn't tell you what to expect. This is what a Fjord looks like, and look, it looks like that. Obviously, in this case, you would go, well, yes, it looks exactly like the thing you just told me it looks like. It does, though. We want them to look like this if it's a Fjord, and one of them does have that. Yay. We want them to look a bit more like this if they're an XOR, minus some of the carbon stuff at the end, which isn't behaving, but we didn't catch this one during outburst. We caught it before and after an outburst, so we think if we got it during the middle, it would look perfect. But still, kind of cool. If we examined it in a bit more detail, with some stats and whatnot, Mike, maybe do the stats. Whenever you have Mike in your paper, you're like, have you considered doing some more statistics, Calum? Which test would you think I should do? Here's one. Fine, I'll go see if there's a Python package for it, and there isn't, and then I have to go and write it myself. Then check that it actually worked, and then learn how to read it. Hassle. Making me do science properly. Mental. Anyway, here are some interesting things that we found. This plot here shows the, basically, YSO slope. For reference, class 1s are everything above that line here, so everything on this side. These ones, well, actually above there, isn't it, actually? So 0.3 upwards. Ones between there and there are flat spectrum, and ones over here are class 2s. Up here is more like the realm of class 0s, which is kind of cool. And the stars that we found, we compared to, so basically the triangles and the squares, are us comparing our Fjord candidates with existing ones, and they do look roughly the same, which is great, except for a few, which you'll notice are in red, for example, that one there. That means instead of getting bluer, they get redder, which is weird. Yes?
How many Fjords did you find?
12.
You said one of them looked like the light blue diagram, as it should. What about the other 11?
Oh, no. 11 of them looked right, one of them didn't.
Oh, I see.
Yeah. Well, actually, 2 of them didn't. And then we also have a few others that we think still might be Fjords, but because of the way science works, because we weren't sure on it in the paper, I can't actually tell you that. But there are, if you want to read the paper, it's open access because you're all British, so you can read it if you're that way inclined. You can make your own decision if what you think they are, and then you can go and tell the referee. You can't. We don't have their email, but that means I don't know who it is. And then, yeah, our XORs look roughly as they should do as well. These are the circles, and they roughly behave as we would expect them to. Bear in mind, it is harder to actually accurately measure the color of those because of the way the light curves worked. That's why I didn't focus the paper on them. This thing here is more interesting. This is a measure of something called structure. Now, what structure is a time series analysis tool normally meant for boring things like the stock market. But what you could do is you can basically measure how frequently your seen changes in variability, your brightness, happens over what time scale. So if you have short time scales, i.e. maybe a month, it will appear on this diagram roughly in the middle. And long time scales would be on this side. And we can see that as we go up in SED class, which are class 2s, flat spectrum sources, class 1s, and then class 1, class 0s at the top, we get more and more long period variability. So long duration is preferentially seen, which would imply we have more of the FUOR type outbursts than the shorter XOR outbursts, which is cool. Basically means the more of the embedded stuff you look at, the more you're likely to find the really high energy sources that have a much bigger impact on planet formation. Because this is the kind of thing that will basically melt the ices that you kind of clump together to form planets. And thus will change where all the different molecules are, molecules that you will need to form life. Will it dissociate them completely? Will it move them outwards? We don't know. But it's worth getting a rough idea on how often this happens. Obviously, there are other reasons to care about this, but the one that we help people at Outreach is about aliens, because aliens are cool. Here is a final science plot, some histograms and everything. Look at how many stats I put on there, Mike. Look at that, it's all stats. There you go, he's happy. Again, same colors as before. These are our youngest, well, less evolved sources. These are the most evolved sources. And we're again looking at how much in the way of amplitude they have, so how big their outbursts are. And we can see that preferentially we find more and more big outbursts the less evolved we get. Good news, and we can back it up with some stats. Obviously this histogram is a lot less untidy, well, a lot more untidy, because we only have 378 sources, as opposed to the top where we had 4,000. But this is, yeah, collectively about 7,000 stars in Cygnus X. Again, it's a very big star cluster. We don't have all of the class 3s, and how many YSOs do you reckon are in Cygnus? Ballpark? Like maybe 12,000 or so?
More than that.
Oh, okay.
Like 60,000.
Oh, loads. So we've only really scratched the surface. But for the rest of them, we need even bigger telescopes to actually basically dig in there and find the rest of them. And it is on that point that I will leave you open to grill me about the nonsense I've just spouted at you for the last hour of my life. And yours.
Thank you, Calum, for the great talk. Do we have any questions?
So what are you going to do next?
I am moving to Valparaiso.
That bit we know.
I'm going to do a collection of different things. I am going to carry on with my own line of research. I have the additional benefit of officially now working for one of my best friends, who is more than happy to let me basically do my own thing, because my own thing is similar to his thing anyway. So rather than being told what to do and being someone's research assistant, I have a lot more leeway as a postdoctoral fellow, as opposed to, it's not a full fellowship. I'm applying for one, but don't know if I'll get it. So I will be trying to do this again, but rather than using one area called Cygnus X, I'm instead going to go step by step across the entirety of the southern galactic plane, because I'm a member of a survey called VVV, which is a near-infrared survey that basically examined and took repeat pictures of the entirety of the southern galactic plane for about 15 years. So I've got tons and tons of light curves to work with, and I can compare the near-infrared behavior to the mid-infrared behavior to really kind of get into the differences. Downside is, while spicy, still a useful catalog, covers the entire sky, I don't have an equivalent embedded catalog, so I have to go through the hassle of making it myself. So I'm going to go star forming region by star forming region to go and dig into those in more detail. But I've still done a statistical sample. I've actually already finished it. I thought common sense is do the work now while I'm still being paid at Hertfordshire for teaching, but I can get a head start on all the research I'm paid to do in Chile. So when I get there, I already have like my first 10 meetings with my boss covered without having to do any work. Nice. Yeah, so that's what I'll be doing, but I'll also be working on 2 upcoming surveys. VVV Renew, where we do the same thing, but more of it and only on the interesting stuff, and VVV KSS, which is a spectroscopic survey where we get spectra we've been awarded 120 nights now on a very, very, very big telescope at Paranal Observatory, which you might recognize the hotel from James Bond Quantum of Solace, because they blew it up. Only they actually didn't. Although I've been told to be scared of the spiders, so now I'm terrified. Thank you for helping with that fear. Just lie. Next time, just lie. And they're like, there's no spiders, Calum, it's fine. But no, so that's the kind of next plan going forward. I've also got some other ideas to investigate a bit more eruptive variability, as well as looking for outflows with one of my other collaborators who's currently based in Bologna.
So how many significant sort of studyable, close enough star formation regions are there?
Oh, I don't know off the top of my head actually. There's a good number, but especially as telescopes get better, the distance isn't so much of a problem. If you want to do really in-depth studies on individual objects, you want them to be fairly close by, which you've got at least 20, 30 that are worth looking at in various scales and ages and sizes. You can also kind of look around protoglobular clusters as well, which are a similar thing. Basically, once you use up all the gas in a nebula, you basically just get a collection of stars all really close to each other with a small amount of gas, and that's called a globular cluster. And there'll still be some young stars forming in there, the smallest ones, because they take ages to make. So there's a good number of things you can look at. Yeah?
So your data sounds really cool, but what is the importance of them? What are their applications?
So applications for you as humans, nothing whatsoever, useless. It's blue sky research. We research it because we want to, and generally governments are happy to keep us around so that when they need us to do actual, useful, important things, we've been placated long enough that we'll help. But there are obviously massive benefits to researching in astronomy, which is mostly about data science and data processing. When we draw in this much data, because space is big and the telescopes we keep asking for keep getting bigger, and then we're like, how do we handle this much data? We have to invent new and better ways to process it quickly and efficiently and accurately. And that leads to massive advances in machine learning, into the internet's infrastructure, as well as parallel computing, processing, and all that jazz. So you do get the benefits down the line. For example, there's no need to really understand the subatomic particles created at CERN, but I think we all can agree the internet is great. So little things like that come out of this line of research. For example, the SKA, which is being built in South Africa, we have to understand how to process petabytes of data daily, which will mean sending across the internet, in the first night of imaging, we will produce more data than the internet has ever processed since it's been invented. And we'll need to know how to do that, because otherwise it'll be money wasted, and then it'll look bad when it comes to grant time. So we'll try and work it out by then. But yeah, also, machine learning it's being used in other industries as well, especially now, but astronomy did popularize it. It was one of the first big fields where we thought it was really going to be useful, and that's not just machine learning and AI. AI comes in a variety of forms, and we found uses for neural networks, for large language models. We found uses for more kind of classification and categorization tools as well, supervised, unsupervised, all that jazz. So yeah, if you're getting replaced by AI, sorry, we probably helped.
From what we've heard this evening, you're going to have a long time studying new stars.
Yeah, they keep making them. It's great.
So what does that indicate for the finite universe?
Well,
is it getting bigger?
The universe is getting physically bigger because that's what dark energy does. But I think it's worth considering the scale of the universe. I am talking to you about stuff that seems big, when in actuality it's in our local neighborhood and it's a very small number of stars. Like our galaxy has, several hundred billion stars in it? And I'm going, hey look, I found 12 new ones. in reality, those numbers don't really add up, and our galaxy is small. We have a very small galaxy. It's not a dwarf galaxy by any stretch, but it's not a normal-sized galaxy. It's quite a lot smaller than usual. So when you deal with the kind of expanse of the universe, things in other galaxies, they are so far away that it's obviously it's not relevant, because it is, and it helps us understand how we make galaxies in the way that we have now seen them. But like the Milky Way is a good few hundred few billion years old, right? It's what, 11, 12 billion years old, Milky Way? So it's only a billion years older than the universe is. But in that billion years, so much happened that we would need to look at earlier galaxies, but later because redshift and the numbers go backwards again. Backwards numbers. Very confusing, but yes. When it comes to the enormity, very little.
How do you view the beginning of the universe then? The Big Bang? Did it happen?
Yes. Because if it didn't happen, we wouldn't have stuff. And we do definitely have stuff because I'm sat on it. Like this table is made of wood. Wood is made of mostly carbon, and if it's made of carbon, that carbon has to be made somewhere, and you can't make carbon without previously having a cloud of hydrogen that exists somewhere, and you had to have that be formed. And the only way you can form that is with a great big explosion, because you can rely on the concept of pair production. Now, we have to ask the particle theorists why we see a universe made entirely of matter, when in theory, when you make it, you have to get matter and antimatter in equal parts, and particle theorists have not solved this. They don't know. This is one of the reasons why I left particle theory. Yeah.
Dark energy.
Dark energy makes the universe expand. It doesn't.
It answers the questions mathematically, but does it exist?
Oh. Who knows?
I can do the maths.
Dark matter.
I can't.
Dark matter definitely does.
Solves a problem.
The question of what it is. Dark energy is there to solve a problem.
Well, the recent findings have actually.
It depends which.
Some of their thoughts on dark energy.
Yes, they did, and
this is the last few weeks.
Yes, yeah. It's not to the level that we thought it was, but equally that could imply, yes, but it's declining in the rate of expansion, not that the expansion is contracting, which is even weirder. It could just be that we measured it wrong the first time though.
Or it's not what we thought it was.
Or there could be more than one thing. You could have dark energy and it's even darker pow. We don't know. And the problem with this all comes from the standard model of particle theory.
Which isn't complete.
It isn't complete and it doesn't work, but every attempt to make it works even worse. This is why I left particle theory, because I sat there working on something called supersymmetry, because it seemed like a great idea at the time, and then your supervisor sits you down and goes, now, they listed the problems with the standard model, and there's not that many. Standard model is pretty good, and it has a few issues. And then you look at the... Pardon?
Newton's pretty good.
Exactly, it was pretty good, but it's not right. Then you look at SUSY and you go, okay, right, so we've solved, with supersymmetry, you solve the dark matter problem because you can pick it out of tables. You can go, yes, these are the particles, here they are. Great, problem solved. The unfortunate reality is, not only does it make a bunch of particles that we can't find, but it also breaks 3 fundamental laws of the universe that we know to be true. And I would argue, when I look at that, it's like, we solved a problem. It's like saying, my house is on fire, I've put it out with water. What have you done? I've buried it in the middle of the Atlantic Ocean. You're like, that's not better, and now I have a pet as a shark. It's now worse than it was. And the same thing with string theory, that requires you to have 14 dimensions. There are 4, so where are the others coming from? You tell me. Depends on which version of string theory you're looking at. More modern versions keep up in number of dimensions, because you go, the 10 one isn't working, and they're like, well, what about 11, 12, 14? Yeah. And then you've got problems with the unit. It's a real challenge, but if you go back as far in energy terms as like what we call grand unification theory, which is just math speak for what if we smash everything together really, 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 really hard? How much energy is there? And the number is silly. I can't remember how many zeros it has after it, but I suspect it's something in the region of 60. Is it 10 to the 60? Something like that, joules, which is insane numbers. And that maybe would make things work, possibly. And if you do that, maybe you have enough particles to make dark energy and its friends, or maybe not. Basically, we don't know, which is why astronomy is great, because I look at the things I can see, and I can tolerate dark matter because I can at least see its effects. I know there must be something there with gravity, and if it obeys with gravity, maybe it will obey with other people's friends in future. Maybe we can make it work with light or electromagnetism in some capacity. We just need to understand how gravity works as a force, which we don't also understand. Because we assume there's a particle for it, no one's ever found it. We even named it and everything, it's called the graviton. We can't find it. We don't know where it is. It's hiding. So get people to CERN and make them do it better. crash particles together harder or faster or more, whichever is easiest.
I have a personal question.
Okay.
I may have missed this in your introduction, but what made you decide to work on young star formation? All the things you now just mentioned in that, which you've decided have probably irked you somehow.
Yes. So the switch to astronomy in general happened. Before I did my master's degree, I was still in Hatfield. I picked up a dodgy contract, and as a result, I would have to pay rent after I was finished with term, and that had annoyed me. I thought I might as well live there, but I need to earn some money. And the department was either get a regular job doing something boring, or I could do a summer project at the office. And luckily we had somebody there who was working on, as it turns out, star formation. Different kind, it was what we call massive star formation, so a bit different. And they were working on this. And Elias, who was just retired from our university, he's like a teddy bear human, he's lovely. And he basically encouraged me to go and do it. So I did it before I even started my master's degree. Went off, did my master's, hated it, came back. And it came to PhD application season, and instead of applying for PhDs in particle theory, which I'd pretty much decided at this point that was not happening, one of my friends had started, who went straight to astronomy, and he'd started doing a PhD, said it was great, and encouraged me to apply. I did, I got there, and because I'd already worked on a summer project doing star formation, which had recently just been published, the week I had my interview, they talked about it in our paper discussion session that day, which is the only reason I think I got a position. I ended up speaking with the supervisor of the person that supervised my summer project. And they had a project going, and they said, yeah, we talked about your paper today, it was great. And he asked me what I did in it, because I was listed near the bottom of the author list. And then I pointed to it and was like, well, I made all these pictures, I did the target selection, I did this, that, and the other. My boss, Phil Lucas, then looked irked because I should have been much higher up the author list than I was on this paper, but nonetheless, he was like, okay. And then I found out a month later that they offered me a position. And thus, it was doing star formation, nominally, and then COVID had to learn a bunch of other things because my project was in Chile, couldn't get there to go and do it, so I had to go trawl the archives for various mysteries, which then led me to do some evolved stars, and then found an entirely new type of star, because nothing made sense, so it must be new. And I found some more of them recently. New paper on that incoming. Although, don't ask my new boss, because he doesn't know I'm working on something that's not star formation, because I'm not funded for that.
Picking up on the point there, I was thinking, to what extent, given how interconnected everything is, does it limit you if you're here or you're in Chile? Are you limited at
it's
all
not really,
nowadays?
nowadays there's not a limitation. It's easier, for Chile personally, it's easier to get telescope time. Chile is a small country in terms of population and in terms of its general number of scientists. The number of astronomers is quite high, but because it's so good for building telescopes, because the mountains are less sacred than other people's mountains, it's in the southern hemisphere, it's easy to get things to and from the coastline, because the coastline is just down the road than mountain, because it's it goes up more than it goes wide. Basically means there's tons of places you can put telescopes, and that, because you put them in Chile, you have to offer Chilean observers lots and lots of telescope time. And they don't need all the stuff that they have, so they then encourage other astronomers to come and join their departments to use up that time. And it's generally easier to get telescope time if you're in Chile on a Chilean telescope than it is to apply with every other European or American. And that basically makes you friends with everyone, because if you can't get your telescope proposal through, or you want it at a different time, well, if you've got a friend in Chile, you can go, any chance you could do some observations for me? And then you get put on papers, and then you learn more and more things, and you build a great big network.
So you're basically doing it for popularity reasons?
Basically, yes. If you don't...
They're really good in astronomy.
Yeah.
Real incredibly good.
They are very good at it, because their students have access to all the people in the world who want to become popular and go to Chile for that purpose. And it basically just means that their astronomers get very, very good. Obviously, they want to stay in Chile and live there, because that's their home. Whereas a lot of people like Anna and Mike previously lived, they were at the university that I'm going to be working at. And it's a general rite of passage. Generally, a lot of astronomers will do time in Chile, especially if you had a fairly small network to start with. It's a great choice because you can build your collaborative network and then get on more projects and then come home. Also, everything out there is cheap, and that's quite nice because you can save money, which, good luck doing that here.
Any more questions?
Yeah.
Yeah.
How easy is it to
get funding now with like being financially?
Very, very, very challenging, and it's getting worse. Like, one of the unfortunate realities, one of the first things that you can, like when it comes to, we need to do a government cut, one of the things that you can reliably do is cut blue sky funding, because it's very hard to sell the general public anyway, and like when it comes to like, either cutting foreign spending or cutting a few astronomers who want something new, it's easier to get rid of. And that does make it a bit more competitive. We'll see how it folds out in the next few years. I know the US just had their budget halved for astronomy last week. We also lost a brand new space telescope that's mostly finished. Quite why they are cutting the funding.
Actually lost it, or are they going to just put it back?
Well, they're probably it's in a hermetically sealed chamber. I imagine when the next government comes in, they'll probably uncancel it, because the first thing American governments do is undo everything the previous one did, so they get nothing done ever.
The rule in NASA is that it's not a real NASA mission until it's been cancelled at least once.
Exactly. Like for example, JWST, which makes some of the images, that image there, that was cancelled once and was bailed out by ESA and Europe. It wouldn't surprise me if the telescope mission that just got canned, which is why have I forgotten its name? Nancy Roman, Space Observatory. Wouldn't surprise me if maybe ESA do something similar and try and bail it out once they are sure that it's being canned. We don't know. But yeah, the US funding's just gotten bad. Chile's funding is always pretty good though, so. And generally in Europe, ESO and ESA, they have good money coming in. So funding should hopefully be fine, but be a bit more challenging. There's so many more jobs for astronomers now, just switching to data science roles in industry, that enough people will go, I want money now, that hopefully the pipeline will still exist and keep people, but if it doesn't, then I guess I'll have to do the same thing. I'll go and work for the man, whoever that is.
So you're talking about how much data is going to come out of the
SKA.
Yeah.
Square kilometre array.
Square kilometre array.
Petabytes.
Whatever. And you haven't yet got a way of processing it.
No.
Presumably that needs to be a kind of
priority.
Enormous increase in computing. Where are all these computers? How is?
We don't know. It's not done.
What?
I mean, I am normally friends with somebody whose job it is. They've basically been going around industry to basically go and see, hey, could you donate some of your ideas to us, and we will make them better and give you back results. But like a lot of this infrastructure is still happening behind the scenes. It's just that because it's computer science, I'm not actively reading the literature for it. So some of this stuff is happening, and they are coming up with new and intelligent ways to store the data, to basically like process it in situ, so that as you process data, it gets smaller. It's like data reduction is a term. Like, you know, even in terms of just general space stuff, I started with 7,000 young stars and all the associated images and processing power from all of that, and I ended up with 48 that I found interesting, with a few PNGs of light curves to go with them. So I took terabyte of data and I turned it into a very small amount. So
you probably didn't throw the terabytes away because you were going to go and look at.
No, I put them in the recycle bin, delete them, gone. I can't have that on my computer. It's too big. It'll make it run slower. How am I supposed to play games in the evening? But I mean, it's still stored somewhere.
Yes.
It's wherever I got it from. But
where's all the end? So we're going to need masses of energy, presumably. They all
yes.
be solar powered. There must be.
I actually don't know what they're going to do for the SKA.
Somewhere.
I would assume
I was thinking,
solar.
Also with like ChatGPT and stuff like that, they've been going on about how much carbon
Oh yeah,
is
it's
going on just
awful.
by people doing those little like doll
Yeah.
images now.
Yeah, the ones that, in our case, we're doing something relatively useful with it, and this kind of data processing will be less intensive than doing anything with AI.
Yeah.
AI stuff is, because it uses GPUs, they're way more energy intensive, they are hungry, and they do tend to make a mess. Whereas we'll be doing mostly CPU processing, which isn't quite as bad.
So, I don't know if it exists in astronomy or not, but I know with biology you have like a central computing system. So you kind of put your job request with the computing. So you have like these 3 repositories in 3 different continents. So the European one is envelop. And so I don't know if you guys
we kind of have a collection of things. If you've got really, really big jobs to do, there are European and American data centers that you can use. But most universities worth their salt will have their own that is a bit smaller but easier to get time on. Like Hearts has a pretty big one. It's based in the library at well, just behind the library in the Haviland campus in Hatfield. And inside there are shed loads of GPUs and CPUs that we can use. Tons of nodes. These are not the kind of ones you can plug into your PC. They are absolutely monstrously powerful, costing £10,000 for a single processor, graphics card or whatever. And they're all linked up together, so we can apply for time and run things on that. But equally, there are other places you can go and run big jobs. But for some things, you can just do it on your own computer and just use it. Like overnight, I'll just leave my laptop on, or at the office, I might, if it's like half an hour before lunch and I want an extended lunch break, technically, if my computer's doing my science for me, I'm still at work. So then I can get an hour and a half for lunch. Quite nice. Or I can sit outside and have a coffee, whilst technically I'm all still working because my computer's doing stuff. And then I come back and check it.
So, I'm going to stop with the questions right now, but I think, you okay?
Yeah, I've just been stood on my foot for long. Yeah.
So I think Calum will be hanging around a little while, and we also have Michael if anybody has any questions.
Well, if you have questions, ask Mike because he's better at it than I am.
You're the speaker. So feel free to ask. And thank you very much.